Monsters exist in the cold depths of space, and they are larger than you can possibly conceive. We are talking about the universe's largest black holes, cosmic giants whose sheer scale and power defy human imagination. By the end of this journey, you will possess a profound understanding of these gravitational behemoths that shape the cosmos itself. We will uncover how something invisible can weigh billions of suns, and what happens if you fall into a darkness wider than our entire solar system. We are diving into 50 mind-blowing facts about these entities, exploring their immense size, terrifying power, and the deepest mysteries they guard. What do you believe is the ultimate fate of everything that crosses their boundary? The very definition of large shifts when we talk about these cosmic giants. To understand the universe's largest black holes, we first need to know what we are measuring. Not all black holes are created equal. The ones you might be most familiar with are called stellar mass black holes. These form when a massive star collapses at the end of its life. They are incredibly dense and powerful, but they are relatively small, typically weighing between a few times and a few dozen times the mass of our Sun. Their event horizon, the point of no return, might be just a few miles across. Now compare that to the true monsters we are exploring. These are the supermassive black holes. They do not form from a single star. They are a different class of entity entirely, residing in the hearts of nearly every large galaxy, including our own Milky Way. Their mass is measured not in solar masses, but in millions or billions of solar masses. That is a 1 followed by 9 zeros. The event horizon of such a beast is not a few miles wide, it is wider than our entire solar system. When we say largest, we are talking about these supermassive black holes, the gravitational anchors of galaxies. Yet the story of size does not end there. Astronomers are now hunting for even more elusive categories like intermediate mass black holes, which could be the missing link, and theorizing about potential ultramassive black holes, whose scale might redefine our understanding of large once again. The numbers we use to describe them are almost as vast as the objects themselves. To grasp the size of these cosmic giants, we need a unit of measurement that matches their grandeur. Astronomers do not use tons or kilograms, they use something called a solar mass. One solar mass is simply the mass of our own Sun. It is a familiar anchor, a star we know, weighing about 2 billion kilograms. Now hold that thought. The supermassive black hole at the center of our Milky Way, named Sagittarius, a star, is about 4 million solar masses. That means it has the equivalent mass of 4 million suns crushed into a single point. That is already a number that strains comprehension, but we are hunting for the largest of the large. The current record holders, black holes like TON 618, have masses measured not in millions but in billions of solar masses. Think about that for a moment. 1 billion, that is a 1 followed by 9 zeros. A billion solar masses means a single gravitational object contains the equivalent mass of a billion stars like our Sun. To visualize this, imagine our Sun, that brilliant, life-giving sphere, shrunk down to the size of a single grape. In this scaled-down universe, a black hole with a mass of 1 billion solar masses would not be a bigger grape. It would have the collective mass of every grape in a mountain range, every peak, every valley, every stone in that entire vast landscape, all compressed into one incomprehensible point of darkness. This is the scale we are dealing with, and it is only the beginning. Our own galactic center is a mere pebble compared to the true titans. Among the giants, one name stands alone as the current heavyweight champion of the known universe, TON 618. This is not just a black hole, it is a hyperluminous quasar, a beacon of terrifying power visible from billions of light years away. At its heart lies the single most massive black hole we have ever measured. Its weight is almost impossible to state without your mind glazing over. Astronomers estimate its mass at 66 billion times that of our Sun. Let that number settle. 66 billion. If our Sun were a single grain of sand, the mass of Ton 618 would be equivalent to a vast, endless desert, a shifting landscape of sand so immense it could bury continents. This mass warps space so profoundly that the boundary of no return, its event horizon, is not a point but a sphere of darkness of stupefying size. This sphere, known as its Schwarzschild radius, spans a distance so large it makes our solar system seem microscopic. The diameter of this dark sphere is over 1,300 times the entire distance from our Sun to Pluto. To put it in a more chilling way, if you could shine a beam of light along the edge of this black hole's event horizon, that light, traveling at the absolute speed limit of the universe, would take weeks, not seconds, not hours, but full weeks to complete a single trip across the void. This is not an object, it is a geographical feature of the cosmos, a hole in reality wider than most star systems, and it is out there, right now, holding court in the distant darkness. Its event horizon is a physical boundary of unimaginable scale. This is not a metaphor, it is a real, calculable sphere in space, a line you could theoretically cross, though you could never return. For Ton 618, the diameter of this sphere of absolute darkness is roughly 1,900 astronomical units. An astronomical unit is the average distance from Earth to the Sun, about 93 million miles. So take that distance and lay it end to end 1,900 times. The resulting sphere is so colossal it does not just dwarf our planetary orbits, it utterly eclipses the entire known structure of our solar system. Think of the Oort cloud, that distant shell of icy debris believed to be the solar system's final frontier. The event horizon of Ton 618 is larger than that entire cloud. If you were to place this black hole where our Sun sits, its event horizon would not just swallow Mercury, Venus, Earth, and Mars. It would not stop at Jupiter or Saturn. It would engulf everything out past Neptune, past Pluto, past the Kuiper belt, and it would keep going. It would comfortably contain every planet, every moon, every asteroid in the main belt, and every single comet in the Oort cloud within its dark embrace with room to spare. All of that familiar cosmic real estate, all the orbits we have mapped and studied, would simply vanish inside a perfect, lightless sphere. This is the true meaning of scale for these giants. Their hunger is not defined by a mouth, but by a geography, a permanent shadow on the fabric of space wider than a star's domain. Yet we know its staggering weight with surprising certainty. How can you possibly weigh an object that emits no light, a shadow in space? Astronomers have become cosmic detectives, using the universe's own laws as their scale. They do not measure the black hole directly. Instead, they observe the frantic dance of everything caught in its gravitational grip. One of the most reliable methods is called stellar dynamics. Picture the heart of a galaxy like our Milky Way. There, stars are not peacefully drifting. They are being whipped around at incredible speeds, tracing tight, elliptical orbits around an invisible focal point. By meticulously tracking the speed and path of these stars over many years, scientists can apply the laws of gravity, the same laws that govern Earth's orbit around the Sun. The faster a star orbits and the tighter its path, the more massive the unseen object at the center must be. It is like watching a child on a playground swing. You cannot see the parent pushing them, but by observing how high and fast the child swings, you can infer the strength and timing of the pushes from the unseen hands. For black holes, those pushes are the relentless, overwhelming pull of gravity. Another powerful technique is gas dynamics. Many supermassive black holes are surrounded by a swirling, superheated disk of gas and dust called an accretion disk. This material does not fall in straight. It spirals like water going down a drain, and it moves at a significant fraction of the speed of light. By analyzing the light from this incredibly hot disk, specifically its Doppler shift, astronomers can map the velocity of the gas at different distances from the center. The speeds they find are so extreme that only the gravity of a billion solar mass object could possibly be the cause. For the most active and luminous black holes, quasars like TUN 618, a method called reverberation mapping is used. Here, scientists monitor the brilliant, fluctuating light from the inner accretion disk. They then measure a slight time delay as that light illuminates clouds of gas farther out. This delay acts like a cosmic echo, allowing them to map the geometry and distance of these clouds, and from that, calculate the black hole's mass with remarkable precision. These are all indirect measurements, but they are built on the unshakable foundation of gravity. We cannot see the monster, but we can see the tremors it causes in the fabric of space, and from those tremors we can deduce its terrifying weight. This changes everything we thought we knew about their purpose. For decades, the popular image of a black hole was a cosmic vacuum cleaner, a mindless devourer of everything in its path. But the truth is far more profound and strangely beautiful. These supermassive black holes are not monsters lurking in the dark. They are the very hearts of their galaxies. Think of a galaxy not as a static island of stars, but as a living, breathing organism. And at its core, providing a rhythmic gravitational pulse, is the supermassive black hole. Our own Milky Way has one, a relatively quiet giant named Sagittarius, a star. Andromeda, our nearest galactic neighbor, has one. As far as we can tell, nearly every large galaxy in the universe does. This is not a coincidence. It is a fundamental relationship, a partnership forged over billions of years. Astronomers now speak of co-evolution. The galaxy and its central black hole grow up together, influencing each other's destiny in an intricate cosmic dance. The black hole's gravity, immense as it is, shapes the orbits of millions of stars in the galactic core, creating a dense, swirling stellar metropolis. But its influence extends far beyond simple attraction. It acts as a cosmic regulator. When a black hole feeds actively, gulping down vast amounts of gas, the process does not just create a brilliant quasar. It also generates unimaginable energy, unleashing powerful jets of radiation and particles that blast outward for thousands of light years. These jets can heat up surrounding gas clouds, preventing them from cooling and collapsing to form new stars. In this way, a supermassive black hole can put the brakes on star formation in its own galaxy, effectively deciding how many new suns will be born. Conversely, by stirring the galactic pot with its gravity, it can also trigger waves of compression in other gas clouds, seeding the birth of new stellar nurseries. So it is not just a destroyer, it is a creator and a governor, a stabilizing force whose presence is essential for the galaxy we see today. Without that dark, silent heart beating at the center, our Milky Way, and every spiral and ellipse in the night sky would be a profoundly different and likely far more chaotic place. Yet for all their terrifying power, the one in our own backyard is surprisingly calm. Meet Sagittarius, a star, the 4 million solar mass black hole sitting at the very heart of our Milky Way galaxy. It is a mere 26,000 light-years away, which in cosmic terms makes it our next-door neighbor. Compared to the ravenous quasars lighting up the distant universe, our central black hole is a gentle giant, a quiet monarch on a mostly empty throne. It is currently starved of material, with only a trickle of gas and dust spiraling into its event horizon. This relative calm is what allows life to exist here in the galactic suburbs. If Sagittarius, a star, were as active as the monster TUN 618, the intense radiation from its accretion disk and jets would likely sterilize entire spiral arms, making our quiet corner of the galaxy uninhabitable. But its quiet nature does not make it any less real. For decades, its existence was a compelling theory, the only explanation for the bizarre motions of stars at the galactic core. Then came proof, work so definitive it earned a Nobel Prize. Astronomers spent years tracking a star known as S2 as it performed a frantic 16-year-long orbit around an invisible point. At its closest approach, S2 screamed through space at nearly 3% the speed of light, a velocity that could only be caused by the gravitational pull of something incredibly massive and incredibly small. That something was Sagittarius, a star. The precise dance of S2 and other stars provided the first direct, irrefutable evidence that a supermassive black hole was not just a concept, but a physical reality anchoring our home galaxy. And in 2022, humanity saw it. The Event Horizon Telescope collaboration, a planet-sized network of radio observatories, unveiled the first ever image of Sagittarius, a star's shadow. It was not the fiery maelstrom of an active quasar, but a serene, donut-shaped ring of light surrounding a central darkness, a silent confirmation of the gentle giant we have long suspected was there. That image is a portrait of our galaxy's silent heart, a darkness that has watched over the Milky Way for billions of years, its gravity the steady hand that guides our cosmic home. That gentle portrait of our own galactic heart was not the first time we saw the unseeable. Years before Sagittarius, a star's shadow was revealed, humanity captured a different kind of monster. In April 2019, the world witnessed a scientific miracle, the first ever direct image of a black hole. The target was not our own quiet giant, but a behemoth in a galaxy 55 million light-years away, known as Messier 87. The black hole at its core earned a simple, legendary name, M87 star. This was the work of the Event Horizon Telescope, a collaboration so ambitious it defied belief. It was not a single telescope, but a network of 8 radio observatories scattered across the globe, from the peaks of Hawaii and Mexico to the deserts of Chile and the frozen landscapes of the South Pole. By synchronizing these dishes with atomic clocks, scientists effectively created a virtual telescope the size of our entire planet, an eye with a resolution sharp enough to read a newspaper in New York from a sidewalk cafe in Paris. What they saw after years of data processing became an instant icon of human curiosity. It was not a photograph of the black hole itself, which is impossible, but of its shadow against the inferno behind it. The image, glowing in fiery oranges and golds, showed a brilliant, lopsided ring of light surrounding a central region of profound darkness. The public lovingly called it the cosmic donut, but that ring was the accretion disk, superheated gas spiraling at nearly the speed of light, its brightness warped by the black hole's immense gravity. The central darkness was the shadow of the event horizon, a silhouette roughly 2.5 times larger than the true point of no return, a dark fingerprint pressed into the fabric of space-time by an object weighing 6.5 billion suns. This single image did more than prove a theory. It transformed black holes from abstract equations in a physics textbook into a tangible reality. For the first time, everyone on Earth could look at that fuzzy, orange ring and know, with absolute certainty, that the monsters were real and we had finally found a way to take their picture. But even the title of supermassive is not enough for the true cosmic royalty. Beyond the well-known category of supermassive black holes lies an even more exclusive class, a designation reserved for the most unimaginably large singularities in existence, the ultramassive black holes. This term is not just scientific flair, it marks a fundamental threshold. An ultramassive black hole is defined as one with a mass exceeding 10 billion solar masses. 10 billion, that is a 1 with 10 zeros. This is not merely a bigger version of the black hole in our galaxy. It is a different order of being entirely. These are the emperors of darkness, and they rule from very specific thrones. You will not find an ultramassive black hole in a graceful spiral galaxy like our Milky Way. They reside almost exclusively in the cores of giant elliptical galaxies, which are themselves the ancient, bloated kings of galactic clusters. These elliptical galaxies are not spinning disks of stars. They are vast, spherical or egg-shaped swarms of older stars, often formed from the violent mergers of multiple smaller galaxies over cosmic time. At the center of such a galactic behemoth, the combined fuel of countless mergers has fed the central black hole to grotesque proportions, pushing it past that 10 billion solar mass limit into the ultramassive realm. TUN 618, our current record holder, is the prime example of this rare class. It sits in the heart of a distant, massive galaxy, a gravitational monument to a history of unimaginable cosmic feasting. These ultramassive black holes may represent a different evolutionary path, one where growth is not steady but explosive, driven by the catastrophic collisions of entire galaxies. They are the ultimate endpoint of galactic cannibalism, silent witnesses to the most violent chapters in the universe's story, and their sheer existence challenges our understanding of how anything can grow so large so fast. The title of largest known black hole is a contested crown, and another challenger looms in the distant cosmos. Deep within the Phoenix cluster, a sprawling metropolis of galaxies over 5.7 billion light-years away, lies a potential king of kings. Astronomers refer to the central galaxy's black hole simply as Phoenix A, and its estimated mass is so staggering it pushes the limits of physics. While TUN 618 holds the confirmed record, measurements of Phoenix suggest it could weigh 100 billion solar masses or even more. That figure is not a typo, 100 billion suns compressed into a single gravitational singularity. If verified, this would not just be larger, it would be in a league of its own, a true outlier whose existence challenges our models of how black holes can grow. But here lies the controversy. Measuring a black hole in such an extreme environment is fraught with difficulty. The Phoenix cluster is one of the most massive and violent galaxy clusters known, bathing in an ocean of superheated gas that glows with the energy of 1 trillion suns. This gas is the key to the measurement and the source of the debate. Scientists study the temperature and density profile of this immense cloud, using X-ray telescopes to see how it behaves. The logic is that the central black hole's gravity must be countering the natural tendency of this hot gas to cool and collapse, creating a delicate balance. By calculating the energy needed to maintain that balance, they can infer the black hole's mass. The numbers that come back are almost unbelievable, pointing toward that 100 billion solar mass figure. But some astronomers caution that other processes, like turbulence from galactic mergers, could be providing the extra heating, meaning the black hole might be smaller, though still monstrously large. This uncertainty is the cutting edge of discovery. What is not in doubt is the sheer power on display. The Phoenix cluster is the most prolific X-ray source in the known universe, and that furious energy is the direct signature of Phoenix A's appetite. Even if its exact weight remains debated, its role is clear. It is the furious engine at the heart of a cosmic forge, its gravity stirring a cauldron of gas so vast it defines the destiny of an entire cluster of galaxies. This invisible boundary is a mathematical line drawn on the universe itself. It is called the Schwarzschild radius, named for the German physicist Karl Schwarzschild, who, while serving on the Russian front during World War I, found a solution to Einstein's new equations of general relativity. His work gave us the first precise description of a black hole's ultimate cage, the event horizon. The concept is elegant in its terrifying simplicity. For any amount of mass, you can calculate a specific distance from its center. If you could compress all that mass inside a sphere of that radius, the gravity at the surface would become so intense that nothing, not even light, could escape. This sphere is the point of no return. The formula itself is deceptively simple, written as R sub s equals 2 times g times m divided by the speed of light squared. You do not need to remember the symbols, just the idea. The radius grows in direct proportion to the mass. Double the mass and you double the size of the event horizon. But there is a critical twist, a reason light itself is trapped. The formula defines the point where the escape velocity equals the speed of light. Escape velocity is the speed you need to throw a rock straight up for it to never come back down. For Earth, that is about 25,000 miles per hour. For a black hole at the Schwarzschild radius, that required speed is the cosmic speed limit, 299,792,458 meters per second. Since nothing can travel faster than light, nothing can achieve that escape velocity. The result is a perfect one-way membrane in space. For a billion solar mass black hole, plugging that staggering mass into the formula gives a Schwarzschild radius in the billions of kilometers. That is not a small pinprick darkness. It is a vast spherical prison of gravity, a hole in the universe so wide it could swallow our solar system whole without a trace. This leads to the most visceral question of all. What would it be like to fall into one of these giants? The answer is not simple, and it depends entirely on the size of the monster you encounter. Let us start with the smaller stellar mass black hole. If you were to approach one, you would experience a truly horrifying phenomenon known as spaghettification. This is not science fiction. It is a direct consequence of gravity's nature. Gravity weakens with distance. Your feet, being closer to the black hole, would feel a stronger pull than your head. This difference in force is called a tidal force, the same kind of force that creates ocean tides on Earth, but unimaginably stronger. Near a small black hole, this tidal force becomes catastrophic long before you reach the event horizon. The pull on your feet would be so much greater than the pull on your head that your body would be stretched into a long, thin strand of atoms, a human noodle. You would be torn apart by the gradient of gravity itself. Now consider falling toward a supermassive black hole like Sagittarius, a star. The experience would be eerily, deceptively different. Because the event horizon is so vast, the change in gravity across the height of your body at that boundary is minuscule. The tidal forces there are gentle. You could theoretically cross the point of no return without any dramatic stretching, without even a noticeable tug. From your perspective, nothing special happens at that invisible line. But do not mistake this for safety. The inevitability of gravity has not changed, only its method. Once across, every path leads inward. You would have time to look back out at the universe, watching it distort into a shrinking circle of light behind you as you are drawn inexorably toward the singularity at the center. There, in that realm of infinite density, the tidal forces would finally catch up to you. No matter how large the black hole, the crushing embrace at its heart is absolute. So while a supermassive black hole offers a more serene entry, the final destination remains the same. A reminder that crossing the horizon is a one-way trip into a physics beyond our comprehension. But the terrifying simplicity of a static black hole is only half the story. The universe abhors stillness, and these cosmic giants are no exception. Most real supermassive black holes are not dormant spheres, they are furious whirlpools. They spin, and this rotation transforms them from simple gravitational pits into engines of unimaginable power. This is described by the Kerr model, named for the physicist Roy Kerr, who solved Einstein's equations for a rotating black hole. The difference is profound. A spinning black hole does not just pull on space, it twists the very fabric of spacetime around it, a phenomenon called frame dragging. Imagine a spoon stirring a pot of thick honey. The honey closest to the spoon is dragged along, forced to move with it. Now replace the honey with the structure of reality itself, and the spoon with a billion solar mass singularity spinning at nearly the speed of light. That is frame dragging. The black hole's rotation pulls spacetime into a swirling vortex around it. This creates a region outside the event horizon called the ergosphere, a flattened, pumpkin-shaped zone where the drag is so powerful that nothing, not even light, can stand still. Every object and particle caught within the ergosphere is compelled to move in the direction of the black hole's spin, like a leaf caught in a cosmic whirlpool. It is within this turbulent region that the black hole's spin becomes a source of usable energy. Theoretically, if you could fire a projectile into the ergosphere and split it so that one piece falls into the black hole and the other escapes, the escaping piece could carry away more energy than you put in, stolen from the black hole's own rotation. This is not just a thought experiment. Nature performs this on a galactic scale. The infalling material from the accretion disk is whipped around by this frame, dragging, channeled and accelerated along the black hole's spin axis. The result is the most spectacular signature of a supermassive black hole, colossal jets of plasma that scream outward at nearly the speed of light, punching through their host galaxies for thousands of light years. Those brilliant lighthouse beams we see in images of quasars and active galaxies are powered directly by the spin of the monster at the core, a testament to the fact that these are not just masses but dynamic, rotating engines that write their signature across the cosmos. The power of a spinning black hole writes its signature across the cosmos in beams of pure energy. These are the relativistic jets, and they are among the most violent and spectacular phenomena in the universe. When a supermassive black hole actively feeds, the material in its accretion disk does not all fall straight in. Intense magnetic fields generated by the swirling, superheated plasma become tangled and amplified. Combined with the frame-dragging vortex of the black hole's spin, these fields act like a cosmic railgun. They channel and collimate some of the infalling material, launching it away from the poles of the black hole in two narrow, oppositely directed beams. The particles in these jets are accelerated to velocities so close to the speed of light that Einstein's theory of relativity becomes their daily reality, hence the name relativistic. We have seen these celestial lighthouses in stunning detail. The iconic image of the black hole in galaxy Messier 87 is encircled by the glow of its accretion disk, but wider radio images reveal its true majesty, twin jets of plasma stretching for at least 5,000 light-years into space, one of them pointing almost directly at us. These are not gentle streams, they are focused tsunamis of matter and energy. They punch through their host galaxy and blast far out into the intergalactic void, sometimes for millions of light-years, shaping the environment on a staggering scale. Where these jets slam into the thin gas that floats between galaxies, they create immense billowing lobes of radio emission, visible across the electromagnetic spectrum. This collision is a cosmic regulator. The jets dump tremendous energy into the surrounding interstellar and intergalactic gas, heating it so intensely that it cannot cool down and collapse to form new stars. In this way, the black hole at the center of a galaxy can effectively put a cap on its own growth, quenching star formation and deciding the future evolution of its entire home. Furthermore, these jets are believed to be the primary accelerators of the universe's most mysterious travelers, ultra-high-energy cosmic rays. These are single atomic nuclei, often protons, hurtling through space with energies millions of times greater than anything produced in our most powerful particle colliders on Earth. Their origin was a puzzle for decades. Now we understand that the unimaginable magnetic forces within relativistic jets are nature's ultimate particle accelerators, capable of firing subatomic bullets across the universe. So the next time you see an image of a galaxy with brilliant, opposing jets, you are not just looking at a pretty light show. You are witnessing the focused fury of a spinning supermassive black hole, a force that cooks galactic gas, stifles the birth of stars, and launches the fastest particles in existence into the eternal dark. The brilliant fury of those jets is the hallmark of a black hole's most spectacular phase. We call these objects quasars, a portmanteau of quasi-stellar radio source, and they are the single brightest persistent objects in the entire cosmos. A quasar is not a star, nor is it the black hole itself. It is the entire energetic region surrounding a supermassive black hole in a state of extreme, gluttonous feeding. Picture the black hole as the monstrous engine at the core of a young galaxy. Around it swirls a vast, thick accretion disk of gas, dust, and shredded stars, a cosmic hurricane of matter spiraling inward. The friction within this disk heats it to millions of degrees, causing it to glow with the intensity of 1 trillion suns, outshining every single star in its host galaxy combined. This is the active galactic nucleus, and when it is this ferociously luminous, we call it a quasar. The very black holes we have been discussing, like the record-holding Ton 618, are quasars. They are not the quiet, dark giants of the modern universe, but adolescents in a growth spurt of cosmic proportions, devouring everything within their gravitational reach. Their incredible brightness, however, comes with a profound twist of cosmic perspective. The light from Ton 618 has traveled for over 10 billion years to reach our telescopes. When we look at it, we are not seeing it as it is today. We are peering back in time to an era when the universe itself was young and chaotic, a period often called cosmic noon, when galaxies were closer together and gas for star formation was abundant. In that ancient, crowded universe, supermassive black holes found a feast laid out before them, growing rapidly and lighting up the darkness with their furious energy. So every quasar we detect is a fossil flash from the universe's wild youth, a beacon from an age when the monsters at the heart of creation were at their most ravenous and radiant. But what happens when one of those cosmic railguns is aimed directly at our planet? We call these objects blazars, and they represent the most extreme and terrifying version of an active galactic nucleus. A blazar is essentially a quasar with a deadly twist. Remember those relativistic jets, the focused beams of plasma and radiation screaming from the poles of a spinning supermassive black hole. In most quasars, those jets point off at some angle into space, but in a blazar, by a staggering stroke of cosmic geometry, one of those jets is pointed almost directly at Earth. This alignment transforms our view completely. Instead of seeing the accretion disk from the side, we are staring straight down the barrel of the universe's most powerful particle accelerator. The effects are dramatic. First, the object appears phenomenally bright, often outshining its entire host galaxy, because the jet's radiation is beamed directly toward us and its intensity is boosted by relativistic effects. Second, its brightness is not steady. It flickers and flares violently across the entire electromagnetic spectrum, from radio waves all the way up to the most powerful gamma rays. These gamma-ray flares can be so intense that a blazar can temporarily become the brightest source of gamma rays in the entire sky, all from a pinpoint of light billions of light years away. This variability is a clue to the chaotic, stormy environment near the jet's base, where magnetic fields snap and reconnect, accelerating particles to unbelievable energies. Because of this, blazars are not just distant curiosities. They are natural laboratories for studying physics under conditions we could never recreate on Earth. They are also key players in a new field of astronomy, neutrino astronomy. Neutrinos are ghostly particles that barely interact with matter, passing through planets like they are not even there. In recent years, detectors buried deep in Antarctic ice have traced high-energy neutrinos back to specific blazars. This means these jets are not just spewing light, they are also producing and launching these elusive cosmic messengers, giving us a direct, if faint, signal from the very heart of the particle acceleration process. To look at a blazar is to have a monster's searchlight swept across the cosmos, illuminating for a brief, brilliant moment the raw, unfiltered power at the edge of a black hole. This popular image of a cosmic vacuum cleaner is one of the most persistent myths in all of science. Black holes do not suck. There is no mysterious force pulling at you from across the galaxy. Their power is simply gravity, the same force that holds you to the ground and keeps the Earth in orbit around the Sun. The only difference is the staggering concentration of that mass. To understand this, consider a simple, mind-bending thought experiment. Imagine our Sun, that brilliant, life-giving star, suddenly vanished. In its place, we instantly substitute a black hole of exactly the same mass, 1.3 million Earths worth of material. What would happen to our planet? The answer is both counterintuitive and profoundly important. Earth would not be instantly slurped into the darkness. Its orbit would not change at all. It would continue tracing the same elliptical path year after year in perpetual night. Why? Because the gravitational pull at our distance depends only on the mass at the center and our distance from it. The Sun could be a star, a black hole, or a giant ball of cotton candy with the same mass, and Earth would feel the exact same tug. The terrifying reputation of black holes comes not from some supernatural suction, but from what happens when you get dangerously close to that unimaginably dense point. The event horizon is simply the line where the escape velocity equals the speed of light. Outside of that boundary, the laws of physics are the familiar ones we know. You could, in theory, orbit a black hole just as you would orbit a star, provided you kept a safe distance. The danger arises from the incredible gradient of gravity near the event horizon, the difference in pull between your head and your feet, which we discussed earlier. So they are not roaming predators hunting for stars to consume. They are more like incredibly deep, still wells in the fabric of space. If you stay away from the edge, you are safe. Only if you stumble and fall in does the well claim you. This corrects the cartoonish image of a black hole as a galactic hoover, wandering through star fields and inhaling everything. They are anchors, not assassins, their fearsome power reserved for those who venture into their innermost sanctum. Gravity is not the only force that writes the rules near a black hole. There is a deeper, more fundamental layer of reality at play, and it creates a paradox that has haunted physicists for decades. This is the black hole information paradox, a puzzle so profound it questions our understanding of reality itself. The story begins with Stephen Hawking. In the 1970s, he made a startling theoretical prediction. Black holes, he argued, are not completely black. Using the strange rules of quantum mechanics in the curved space near an event horizon, Hawking showed that black holes should emit a faint glow of particles, now called Hawking radiation. This radiation carries away energy, meaning the black hole slowly loses mass. Over unimaginable eons, a black hole would evaporate, shrinking until it potentially vanishes entirely. This was a revolutionary idea, but it birthed a terrifying problem. Quantum mechanics, the rulebook for the subatomic world, has one sacred principle: information cannot be destroyed. It can be scrambled, hidden, or transformed, but never erased. Think of burning a book. The ash and smoke seem like a loss, but in principle, if you could track every particle and its state with perfect precision, you could reconstruct the original book. The information is preserved. Now consider matter falling into a black hole, a book, a star, an entire planet. That matter carries information, the specific arrangement of its particles. According to Hawking's calculation, the radiation leaking out is random, thermal noise. It carries no imprint of what fell in. If the black hole eventually evaporates and disappears, where did that information go? It seems to be permanently erased from the universe, a direct violation of quantum law. This is the information paradox. On one side stands general relativity, which says the information is crushed into the singularity and gone. On the other stands quantum mechanics, which says that is impossible. Both theories are pillars of modern physics, yet they give contradictory answers. For half a century, this conflict has driven theorists to the edge of knowledge, suggesting that our picture of the event horizon, or perhaps spacetime itself, is fundamentally incomplete. The fate of information inside a cosmic giant is not just a technicality, it is a battle for the soul of physics, and its resolution may rewrite the universe's deepest rules. Stephen Hawking's insight revealed a ghostly leak in the universe's most perfect containers. Hawking radiation is the process by which a black hole can, over incomprehensible timescales, evaporate. To understand this, we must venture into the bizarre quantum foam that underlies all of space. Even in a perfect vacuum, empty space is not truly empty. It is a seething, turbulent sea of virtual particles. These are particle-antiparticle pairs, like electrons and positrons, that spontaneously blink into existence using borrowed energy from the quantum field. They exist for an immeasurably short moment before annihilating each other, paying back the energy loan and vanishing. This happens everywhere all the time. Now place this quantum froth right at the edge of a black hole's event horizon. Here, the extreme gravity warps the rules. Sometimes, a virtual particle pair will pop into existence so that one particle appears just outside the horizon and its partner appears just inside. The particle inside is forever trapped, but the particle outside, if it has enough velocity, can escape into the universe. From our perspective, the black hole has just emitted a particle. But energy cannot be created from nothing. The escaping particle takes real energy with it. To balance the cosmic books, that energy is stolen from the black hole's own mass. In effect, the black hole has paid for the creation of the particle pair with a tiny fraction of its being. This is Hawking radiation, a slow, quantum mechanical bleed of mass. For a typical stellar mass black hole, the temperature of this radiation is almost unbelievably cold, a tiny fraction of a degree above absolute zero. The process is so slow that it would take many orders of magnitude longer than the current age of the universe for such a black hole to evaporate. But for the supermassive and ultramassive giants we have been discussing, the story is even more extreme. Their Hawking radiation temperature is far, far colder, vanishingly close to absolute zero. Meanwhile, the universe is bathed in the cosmic microwave background radiation, a leftover glow from the Big Bang with a temperature of about 2.7 degrees above absolute zero. This background radiation is warmer than the Hawking radiation of any supermassive black hole. This means these cosmic giants are currently absorbing more energy from the universe's ambient heat than they are losing through their own quantum glow. They are not evaporating, they are growing, however slowly, feasting on the faint warmth of creation itself. Their final evaporation is a fate reserved for a universe so old and cold that all stars have died, and even this background glow has faded to nothing. A timeline so vast it makes billions of years seem like the blink of an eye. Their eventual evaporation is a story for a cold, dead universe, but their birth is a mystery from a hot, young one. How did these billion solar mass giants appear so early in cosmic history? We see quasars, ferociously bright black holes, shining from an era when the universe was less than 1 billion years old. For a black hole to reach that staggering size so quickly, it needed a massive head start. This is the black hole seed problem, and it is one of the great open questions in astrophysics. A supermassive black hole cannot just appear. It must grow from a smaller seed, feasting on gas and stars over time. But the timeline is impossibly tight. Even if it fed at the maximum theoretical rate, a process called Eddington limited accretion, starting from a stellar mass black hole of, say, 100 suns, it could not reach 1 billion solar masses in under 1 billion years. The seed had to be enormous from the very beginning. So what could plant such a colossal seed in the infant cosmos? Astronomers have several compelling and strange candidates. The first is the direct collapse of a primordial giant gas cloud. In the early universe, before the first stars ignited, vast clouds of pure hydrogen and helium could have existed without fragmenting into many smaller stars. If such a cloud, weighing perhaps 100,000 suns, collapsed directly under its own gravity, it might bypass the star stage entirely and implode straight into a massive black hole seed. This would be a monster from birth. A second possibility involves the first generation of stars, known as population 3 stars. These pioneers were likely behemoths, hundreds of times more massive than our Sun. They lived fast, burned hot, and died young in spectacular supernova. The collapse of a single, truly gargantuan member of this first stellar family, or the collision and merger of several of them, could leave behind a black hole seed tens of thousands of times more massive than any formed today. Finally, there is a more exotic idea: primordial black holes. These would not be born from stars or gas clouds at all, but from the intense, uneven pressures in the first fractions of a second after the Big Bang. Tiny, dense knots in the fabric of the newborn universe could have directly collapsed into black holes of almost any size. Some of these could have been the perfect seeds, scattered throughout the cosmos like cosmic landmines, ready to grow into the giants we see today. The truth is, we do not yet know which path or combination of paths nature took. Each possibility leaves a different fingerprint on the early universe, a clue we are only now learning to read. The collision of galaxies is a slow, majestic dance of destruction and creation. When two spiral galaxies like our Milky Way and Andromeda are drawn together by gravity, they do not simply crash like cars. They pass through each other, their stars so far apart that direct collisions are rare, but their immense clouds of gas and dust slam together, triggering fireworks of new star formation. And at the heart of this cosmic ballet, something inevitable begins. Each galaxy brings its own supermassive black hole, millions or billions of solar masses strong. As the galaxies merge and settle into a new, larger elliptical galaxy, these two dark hearts begin a final, intimate waltz. Dragged by friction with surrounding stars and gas, they sink toward the center of the new galactic core. They form a binary pair, orbiting each other in a tightening spiral that can last for millions of years. This dance is the prelude to the universe's most violent single event, a black hole merger. When they finally come together, the collision is not of matter, but of pure spacetime geometry. Two bottomless pits in reality slam into one another, becoming a single, larger pit. The energy released in that final moment is beyond comprehension, but unlike a supernova, this cataclysm does not primarily release light. It unleashes something more fundamental, a shudder in the fabric of the cosmos itself, a gravitational wave. Gravitational waves are ripples in spacetime, predicted by Einstein over a century ago. Think of spacetime not as a static stage, but as a flexible trampoline. A massive object like a star creates a dip. Now imagine two incredibly heavy balls, our black holes, spinning around each other at nearly the speed of light on that trampoline. Their furious motion creates not just dips, but propagating waves that stretch and squeeze the trampoline fabric as they travel outward. These are gravitational waves. They are not made of particles, they are waves in the geometry of reality, stretching and compressing everything in their path, including the space between atoms. For decades, they were just a theory. Then, in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history. It detected the chirp, the literal sound converted from data, of two stellar mass black holes merging over 1 billion light-years away. The signal was a perfect match to Einstein's predictions, confirming that these ripples are real. But LIGO instruments are tuned for the high-frequency waves from smaller black holes, mergers lasting fractions of a second. The merger of two supermassive black holes is a different beast entirely. Their dance is slower, deeper, and far more powerful. The gravitational waves they produce are of a much lower frequency, with wavelengths so long they can span entire solar systems. These waves are not detectable from the ground, as Earth's own vibrations drown them out. To hear the deep bass note of a supermassive merger, we must go to space. This is the mission of the Laser Interferometer Space Antenna, or LISA, a future observatory that is pure ambition. Imagine 3 identical spacecraft flying in a perfect triangular formation, trailing Earth in its orbit around the Sun. Each side of the triangle will be 2.5 million kilometers long, connected not by metal but by laser beams. These lasers will measure the distance between the spacecraft with phenomenal precision. When a gravitational wave from a distant supermassive black hole merger passes by, it will ever so slightly stretch and squeeze the space between the satellites, changing the length of the laser links by a distance smaller than the width of an atom. By monitoring these changes, LISA will listen to the low-frequency gravitational symphony of the universe. It will hear the final months, years, even decades of the in-spiral of black holes weighing billions of suns, culminating in that final, universe-shaking collision. This will not just be about detecting waves, it will be about mapping the population of these dark giants throughout cosmic history, understanding how they grew through mergers, and witnessing the most energetic events since the Big Bang itself. The silent dance of two invisible titans will finally have a sound, and it will rewrite our story of the cosmos. The silent symphony of merging giants is a song we are just learning to hear. While ground-based observatories like LIGO catch the final, high-pitched chirp of stellar mass black holes colliding, the deep bass notes of the universe's largest mergers require a different kind of ear. They sing at frequencies too low for any Earth-bound instrument, their waves stretching and squeezing space over timescales of months or even years. To tune into this cosmic bassline, we must leave our planet's vibrations behind. This is the revolutionary promise of the Laser Interferometer Space Antenna, LISA. Approved by the European Space Agency with NASA collaboration, LISA is not a telescope in any traditional sense. It is a gravitational wave observatory of breathtaking scale and precision, designed to float in the quiet of interplanetary space. The concept is as elegant as it is ambitious. 3 identical spacecraft will fly in a vast triangular formation, trailing Earth in its orbit around the Sun. Each arm of this triangle will span 2.5 million kilometers, a distance roughly 6 times that from the Earth to the Moon. These spacecraft will not be connected by wires or struts, but by laser beams of unimaginable stability. Their sole mission is to measure the distance between each other with a precision so fine it defies belief, sensitive to changes smaller than the width of a single atom. When a gravitational wave from a pair of merging supermassive black holes billions of light-years away washes through the solar system, it will minutely distort the fabric of space itself. For a moment, the distance along one arm of LISA triangle will stretch, while the distance along another will compress. The laser beams linking the spacecraft will detect this infinitesimal wobble, translating the warping of spacetime into a signal we can analyze. What we will hear is not a brief chirp, but a long, rising siren song. LISA will detect the mergers of supermassive black holes not in their final second, but decades or even centuries before they collide. It will capture the entire in-spiral, the slow, tightening dance of these titans as they radiate energy away in gravitational waves and spiral toward their inevitable union. This data will be a treasure trove. By analyzing the waveform, the specific pattern of the siren song, scientists will be able to measure the masses and spins of the black holes with incredible accuracy, mapping out the population of these dark giants across cosmic time. We will effectively be listening to the era of galaxy formation itself, hearing the mergers that built the giant elliptical galaxies we see today. Furthermore, these extreme events will serve as the ultimate laboratory for testing Einstein's theory of general relativity. The space around 2 merging billion solar mass black holes is the most violently curved environment in the universe, a place where gravity operates at its absolute limit. Any tiny deviation from Einstein's predictions, any whisper of new physics, would be imprinted on the gravitational waves LISA hears. This mission will open an entirely new sense with which to perceive the cosmos, turning the silent, invisible collisions of the universe's largest structures into a symphony we can finally understand. This profound simplicity is known as the no-hair theorem. In the face of such cosmic complexity, it presents a startlingly elegant idea. A black hole, for all its terrifying power and the chaotic feast that created it, is fundamentally simple. It has no hair, a physicist's shorthand meaning it has no distinguishing features, no frizz, no unique style. According to this theorem, you can completely describe any black hole in the entire universe using just 3 numbers and 3 numbers only. The first is its mass, how much it weighs. The second is its electric charge, though in reality most black holes are thought to be nearly neutral. The third is its spin, how fast it is rotating. That is it, everything else is erased. Think of the most complex object you can imagine, a star with intricate magnetic fields, a planet with mountains and oceans, or an entire civilization with its history and art. If all of it were to fall into a black hole, the black hole itself would not remember any of those details. The specific arrangement of atoms, the chemical compositions, the beautiful structures, all of that information is lost to the outside universe. The resulting black hole would be indistinguishable from one that formed from a pure, featureless cloud of hydrogen of the same total mass, charge, and spin. This is the ultimate act of cosmic simplification. The black hole becomes a perfect blank slate, defined not by what went in, but by the 3 fundamental imprints it leaves on the fabric of spacetime. Its mass tells spacetime how deeply to curve. Its spin tells spacetime how violently to twist. Its charge, if it has one, tells the electromagnetic field how to arrange itself. Every other detail is swallowed, hidden behind the event horizon, contributing to the whole's total heft and rotation but leaving no other trace. It is a paradox of stunning beauty that an object capable of creating the most brilliant and intricate structures in the cosmos, the swirling disks and the galaxy-spanning jets, is itself a prisoner of sublime and minimalist geometry. That elegant simplicity of a lone black hole is rarely what we see through our telescopes. More often, we witness a riot of light and fury. These spectacular displays belong to a single, vast family known as active galactic nuclei, or AN. Think of a supermassive black hole not as a solitary object, but as the engine of a cosmic power plant. Whether that plant appears as a brilliant quasar, a flickering blazar, or a galaxy with majestic radio jets depends almost entirely on 2 things: our viewing angle and how much fuel is being fed into the furnace. This realization, called the unified model of AGN, is one of the most important ideas in modern astronomy. It tells us that the dizzying variety of active galaxies in the sky are not fundamentally different beasts, but the same beast seen from different seats in the cosmic arena. At the center of every AGN is that supermassive black hole, surrounded by a swirling accretion disk of superheated gas. Around this disk, often hidden from direct view, is a thick, donut-shaped ring of cold gas and dust called the torus. Whether we see the blinding light of the accretion disk itself, or just the glow of gas clouds lit up by its radiation, depends on if we are looking face-on over the top of the torus or edge-on through its obscuring wall. The most luminous of all, quasars, are what we see when we have a nearly face-on view of a black hole engine that is feasting at a tremendous rate. Their accretion disks shine with the light of a trillion suns, outshining their entire host galaxy. If that brilliant core is partially obscured by the dusty torus, we might classify it as a different type of AGN, like a Seyfert galaxy, which has a bright nucleus but the host galaxy is still visible. And then there are the radio galaxies and blazars, where the key feature is those powerful relativistic jets. If the jets are pointing mostly sideways from our perspective, we see the magnificent, billowing lobes of a radio galaxy. But if, by chance, one of those jets is aimed almost directly at Earth, we are staring down the barrel of the universe's most powerful particle beam, and we call that a blazar. So a quasar, a blazar, a Seyfert, and a radio galaxy could, in theory, be the exact same object. An alien astronomer viewing it from a different angle in space would give it a completely different name. This unified model brings order to the celestial chaos, revealing that for all their varied appearances, these are just different masks worn by the same ancient, hungry heart. The unified model reveals a hidden truth that the brilliant fury of a quasar is not a permanent state but a temporary feast. For all their power, these giants can fall silent. When the flow of gas into the galactic center slows to a trickle, the superheated accretion disk simply starves and fades. The brilliant light of the quasar winks out, the relativistic jets sputter and die, and the supermassive black hole enters a dormant phase, becoming quiescent. It is still there, its gravity still anchoring the galaxy, but it emits almost no light or radiation of its own. Our own Sagittarius, a star, is the perfect local example of this cosmic slumber. It is a quiet giant, its event horizon a dark shadow against the radio glow of our galactic center, fed only by wisps of gas and the occasional unlucky star. But its calm is likely a recent chapter in a long life. Evidence suggests that just a few million years ago, a geological blink of an eye, Sagittarius, a star, might have been a low-level active galactic nucleus, its jets painting the nearby Magellanic Stream with a faint echo of its past power. This dormancy is not an end but a phase in a billion-year cycle. The black hole is simply waiting, and the universe has a way of delivering meals. A close passing star straying too near the galactic core can be torn apart by tidal forces in a spectacular event called a tidal disruption event, sending a temporary flare of light and a fresh stream of gas spiraling inward. Or a massive cold cloud of molecular gas drifting through the interstellar void could be captured by the black hole's gravity, crashing down to reignite the dormant engine. A sleeping giant can always be awakened, and when it is, the galaxy itself takes note, as a new chapter of light and energy begins at its silent heart. A dormant giant can be awakened by a single, catastrophic mistake. Picture a star much like our own sun, orbiting peacefully in the crowded core of its galaxy. Its path is stable for billions of years until a subtle gravitational nudge from a passing star alters its course just enough. Over millennia, its new orbit brings it spiraling ever closer to the invisible monster at the galaxy's heart. There is a critical distance known as the tidal radius. If the star passes outside this line, it may survive, though stretched and heated. But if it crosses inside, the difference in gravity between the side facing the black hole and the side facing away becomes overwhelming. The star is not sucked in whole, it is shredded. This is a tidal disruption event, one of the most violent and luminous spectacles in the universe. The star is stretched into a long, thin strand of superheated plasma, a process called spaghettification. About half of this stellar material is flung out into the void on hyperbolic orbits, lost forever. The other half, however, becomes ensnared by the black hole's gravity. This debris does not fall straight in. It forms a chaotic, swirling maelstrom around the event horizon, a temporary and incredibly bright accretion disk. The friction within this disk of stellar gas heats it to millions of degrees, causing it to flare with the intensity of billions of suns. For a few brief months, this single event can outshine every star in its host galaxy combined, a brilliant beacon signaling a black hole's meal. Astronomers hunt for these flashes across the cosmos, not just for their spectacular violence, but for what they reveal. A tidal disruption event is a cosmic lighthouse, illuminating otherwise invisible and dormant supermassive black holes in quiet galaxies. By studying the light curve, the specific way the flare brightens and fades, scientists can weigh the black hole and understand the physics of its sudden, gluttonous feast. It is a stark reminder that even in silence, the monster is always waiting, and a single misstep can light up the dark. Their monstrous size demands a specific kind of galactic throne. There is a striking cosmic correlation, a rule written in the silent architecture of the universe. The largest black holes, the ultramassive ones weighing tens of billions of suns, are almost never found in graceful spiral galaxies like our Milky Way. They reside instead in the hearts of giant elliptical galaxies. These are not the spinning pinwheels of stars we often picture, but vast, ancient, and often featureless swarms. They resemble colossal, golden beehives or fuzzy footballs of older, redder stars, sitting like monarchs at the very centers of the densest galaxy clusters in the cosmos. Think of the black hole M87 star, the first one we ever imaged. Its home, Messier 87, is a perfect example, a giant elliptical that dominates the Virgo cluster. Or consider the Phoenix cluster's central galaxy, host to the potentially 100 billion solar mass behemoth. That, too, is a giant elliptical. This is not a coincidence. It is a direct result of a violent life story. A spiral galaxy like ours is relatively quiet, its growth slow and steady. But a giant elliptical is a cosmic trophy hall built from the remains of countless mergers. Over billions of years, in the crowded downtown of a galaxy cluster, spiral galaxies are drawn together by gravity. They collide and merge, their stars stirred into a chaotic soup that eventually settles into that smooth, elliptical shape. With each merger, the supermassive black holes at their cores are dragged toward the new center. They eventually spiral together and combine, creating a single, more massive black hole. Furthermore, these catastrophic collisions funnel unimaginable amounts of gas and stars directly into the central engine. It is a perfect recipe for creating an ultramassive monster, a black hole fed by the combined feasts of entire galaxies. So when we locate one of these quiet, golden giants floating at the heart of a dense cluster, we are looking at the final, serene chapter of a long history of cosmic violence, and we know that within its core lies one of the universe's largest singularities, a silent testament to the feasts of the past. Even a cosmic giant cannot grow forever without consequences. Physics itself imposes a check on their appetite, a concept known as the Eddington limit. This is a fundamental principle of balance, not for the black hole itself, but for the fiery maelstrom that feeds it. Picture the brilliant accretion disk, that swirling hurricane of superheated gas. As matter spirals inward, it releases a torrent of radiation, a flood of light and energy. This radiation exerts an outward pressure, pushing against the very gas that is trying to fall in. The Eddington limit is the point where this outward push of radiation perfectly balances the inward pull of gravity. It is the maximum brightness, and therefore the maximum feeding rate, that a steady accretion disk can sustain. If a black hole tries to eat faster, the resulting radiation becomes so intense it blows away the surrounding gas cloud, cutting off its own food supply. It is a cosmic diet enforced by its own brilliance. This self-regulation suggests there might be a soft upper limit to how large a black hole can grow through steady accretion alone. Astronomers call this the quasar limit, and current models place it somewhere between 50 and 100 billion solar masses. Beyond this point, the radiation from even the most efficient feeding would be so fierce it could prevent further growth, essentially starving the giant of new material. This theoretical ceiling helps explain why we have not found black holes significantly larger than our current record holders. They may have reached a state of equilibrium where their hunger is matched by their own blinding light, a stable but ultimate size for a solitary feeding monster. This cosmic thermostat has a name: active galactic nucleus feedback, and it is the final piece of the puzzle linking a black hole's life to its galaxy's fate. The relationship is not one-sided. Just as the galaxy feeds the black hole gives back, but its gift is one of violent regulation. When a supermassive black hole feeds actively, the incredible energy it releases does not just create a brilliant quasar. It floods the surrounding galaxy with radiation and, more importantly, channels vast power into those relativistic jets. These jets act like cosmic blowtorches, plowing into the reservoirs of cold gas scattered throughout the galaxy. This cold, dense gas is the raw material for new stars. When the jets slam into it, they do two things. They heat the gas so intensely it cannot cool and collapse under its own gravity, and they can physically push it out of the galaxy entirely, stripping away the galaxy's future fuel supply. This process is AGN feedback. It is a self-regulating cycle. A burst of black hole activity shuts down star formation by removing the gas. With star formation quenched, less gas is eventually available to fall back onto the black hole, so its activity subsides. The galaxy enters a quiet phase. This elegant, if violent, loop explains one of astronomy's long-standing mysteries: why the most massive galaxies in the universe are often red and dead. They are filled with older, redder stars, with no young, blue stars being born. They ran out of gas quite literally, and the central black hole was the primary agent. It blew out the nursery. This makes the supermassive black hole more than an anchor or an engine. It is a governor, a cosmic thermostat that prevents its galaxy from growing too large too fast. Without this feedback, galaxies might burn through their gas in a frenzy of star formation, leaving behind a different, perhaps less structured universe. The monster at the center does not just live in the galaxy, it sculpts its destiny, ensuring a balance between chaos and order on a scale of billions of years. Just across the cosmic street, another silent giant holds court. The Andromeda Galaxy, our closest major galactic neighbor, is a spiral island of 1 trillion stars, a mirror to our own Milky Way. And at its heart, as expected, lies a supermassive black hole known as M31 star. This dark heart is no gentle slumberer like our Sagittarius A star. It is a more substantial and restless monarch. Astronomers estimate its mass at around 100 million solar masses, making it more than 20 times heavier than the black hole in our own galactic center. This greater mass suggests a more violent past, a history of greater feasting or perhaps more frequent mergers with smaller satellite galaxies. We know it is there because of the frantic dance of stars around it, stars that whip around the invisible focal point at speeds exceeding 3 million miles per hour. These stellar orbits, meticulously mapped over years, paint a precise picture of the gravitational monster they circle. M31 star is not currently a brilliant quasar, but it is not entirely quiet either. Observations have detected faint, flickering ultraviolet and X-ray emissions from its vicinity, hinting at a small, sputtering accretion disk, a sign it still receives a meager trickle of interstellar gas. This makes it a fascinating intermediate case, more active than our own black hole, but far from the furious behemoths of the early universe. Its presence sets the stage for the most predictable cosmic collision in our future. In roughly 4 to 5 billion years, the Milky Way and Andromeda, drawn together by their mutual gravity, will begin a slow, majestic merger. Their spiral structures will be torn apart, their stars scattered into a new, elliptical galaxy often nicknamed Milkomda. And during this billion-year-long ballet, the two supermassive black holes, Sagittarius A star and M31 star, will begin their own inevitable dance. Dragged toward the new galactic core by friction with stars and gas, they will form a binary pair, orbiting each other for millions of years before finally spiraling together in a cataclysm that will shake the fabric of spacetime with gravitational waves. The future of our galactic heart is not eternal silence, but a final, violent union with its nearest rival, a merger written in the stars long before our sun even ignited. Between the stellar mass ghosts and the galactic supergiants lies a profound cosmic silence. The universe seems to have skipped a step. We have the small black holes born from dying stars, and we have the billion solar mass titans anchoring galaxies, but what about the middle children? Where are the black holes weighing a few thousand or a few 100,000 suns? Their existence is one of the most compelling mysteries in modern astronomy, a missing link in the evolutionary chain of cosmic giants. These are the intermediate mass black holes, often called IMBHS, theorized to have masses between 100 and 100,000 solar masses. They represent a crucial bridge. They could be the primordial seeds from which supermassive black holes grew, the building blocks of the monsters we have been discussing. Without them, our story has a glaring gap. How did the first quasars grow so large so fast unless they started from a massive seed, something far larger than a single collapsed star? An intermediate mass black hole is the perfect candidate, a head start of tens of thousands of solar masses planted in the early universe. Yet for decades, finding one was like searching for a single dark pebble on an endless starry beach. The evidence was tantalizing but indirect whispers in the data. Some of the strongest hints come not from galactic centers, but from ancient, dense balls of stars known as globular clusters. These spherical swarms orbiting galaxies like distant moons are relics from the universe's youth. In several of these clusters, astronomers have observed stars orbiting an invisible, common point with surprising speed, suggesting a central mass of a few thousand suns. The only plausible explanation is a dark, compact object, an intermediate mass black hole holding the cluster's core together. Other clues come from unusual, ultra-luminous X-ray sources spotted in nearby galaxies. These are point-like objects shining with the X-ray power of millions of suns, far too bright to be explained by a typical stellar mass black hole. They could be intermediate mass black holes in the process of feeding, their brighter glow betraying their greater mass. The hunt for these missing links is now a major frontier. Confirming their existence would do more than fill a catalog gap. It would validate a key chapter in the life story of every supermassive black hole, revealing how the first seeds were sown in the fertile darkness of the early cosmos. The hunt for missing links leads us to an even deeper cosmic shadow, the mystery of dark matter. We know dark matter exists because we see its gravitational hand shaping galaxies and bending light, yet for a century, its true identity has remained hidden. Could the answer be linked to the very monsters we have been exploring? This is a speculative but thrilling frontier, the idea that black holes themselves or their influence might be entangled with dark matter. One bold hypothesis suggests that dark matter is not a sea of exotic particles, but a vast population of ancient tiny black holes, forged in the furnace of the Big Bang itself. These would be primordial black holes, not born from stars, but from the intense density fluctuations in the first chaotic moments of creation. They could range in size from the mass of an asteroid to that of a planet, or even to the missing intermediate mass scale. For a time, this idea was a compelling candidate, a single elegant solution to two cosmic puzzles. However, most observational constraints have now closed the door on this possibility as the primary explanation. Microlensing surveys, which watch for the brief brightening of a star as a dark object passes in front of it, have not found enough of these small, wandering black holes to account for all the dark matter we observe. The universe would be a far more violent place, with constant stellar disruptions and gravitational wave signals we do not see, if dark matter were primarily made of these ancient, compact objects. Yet a small population of asteroid mass or intermediate mass primordial black holes is still possible, hiding in the dark halos of galaxies, a ghostly remnant of the universe's violent birth. A different and perhaps more likely connection lies in the environment around black holes. Some theories propose that dark matter, whatever it is, could be gravitationally attracted to and accumulate around supermassive black holes. Imagine the dark matter halo of a galaxy as a vast, diffuse cloud. At the galaxy's center, the black hole's immense gravity would act as a trap, pulling in these elusive particles and creating a dense spike or cusp of dark matter around the event horizon. This concentrated dark matter could then annihilate with itself if it is made of particles and antiparticles, releasing energy, or it could simply add to the black hole's mass through accretion. In this scenario, dark matter would not be the black hole, but its fuel, a hidden source of sustenance that could help explain how these giants grew so large so quickly in the early universe. While still speculative, this interplay between the darkest things we know and the darkest things we do not know represents a fascinating intersection of mysteries, where solving one could illuminate the other in ways we are only beginning to dream. Our own galaxy holds echoes of a more violent youth. Sagittarius, a star, the gentle giant at our core, has not always been this quiet. Its slumber is a recent chapter in a long and turbulent life, and the evidence of its past outbursts is written across the sky in structures so vast we only recently learned to see them. Look up far beyond the band of the Milky Way into the seemingly empty space above and below the galactic plane. There, spanning a staggering 50,000 light-years from end to end, are the Fermi bubbles. These are colossal, symmetrical lobes of superheated gas, glowing faintly in the most energetic form of light, gamma rays. They balloon outward from the galactic center like the imprint of a cosmic hourglass, a pair of ghosts from a long-ago explosion. Their sheer scale is breathtaking, each bubble large enough to contain our entire visible galaxy. Their existence tells a clear story. Roughly 2 to 4 million years ago, Sagittarius, a star, woke up. It was not a full-blown quasar, but it entered an active phase, likely fueled by a sudden influx of gas. As it fed, it unleashed powerful jets or a tremendous wind of radiation and particles, blasting outward perpendicular to the galactic disk. These outflows punched through the thin halo of our galaxy, heating the gas there to millions of degrees and creating the immense bubble-shaped cavities we see today. They are fossils of our black hole's last major meal, a remnant of its power still lingering in the form of high-energy particles trapped within those vast structures. But the evidence does not stop there. Far beyond our galaxy's immediate neighborhood, a faint river of gas known as the Magellanic Stream arcs across the southern sky. This ribbon of hydrogen is being torn from our two small satellite galaxies, the Large and Small Magellanic Clouds, as they orbit the Milky Way. Yet something about this stream has long puzzled astronomers. Parts of it are strangely ionized, meaning its atoms have been stripped of their electrons, a process that requires a powerful source of energy. For decades, the source of this ionization was a mystery. Now, the leading suspect is our own galactic center. The timing aligns perfectly. A few million years ago, when Sagittarius, a star, flared and inflated the Fermi bubbles, it would have also sent a flash of intense ultraviolet and X-ray radiation screaming out into intergalactic space. That flash, lasting perhaps 300,000 years, would have washed over the Magellanic Stream like a cosmic camera flash, ionizing its gas and leaving it in the energized state we observe today. This means the quiet darkness we perceive at our galaxy's heart is an illusion of our brief human timescale. On cosmic clocks, it was only yesterday that Sagittarius, a star, was an active engine, its light reaching out to touch satellite galaxies millions of light-years away, its fury sculpting the very atmosphere of the Milky Way itself. We live in the calm after a storm, surrounded by the silent, monumental ruins of our black hole's past. The immense gravity of a black hole does not just trap light, it can also bend its path, creating a natural telescope of staggering power. This phenomenon is called gravitational lensing, a direct prediction of Einstein's general relativity. Massive objects warp the fabric of spacetime around them, and light traveling along that warped fabric must follow a curved path. A supermassive black hole is the ultimate warp, a bottomless pit in reality. When such a black hole passes in front of a more distant star or galaxy from our perspective, its gravity acts like a cosmic lens. The light from the background object is bent and distorted as it travels around the black hole's immense gravitational field on its way to our telescopes. The results can be breathtakingly strange. Instead of seeing a single, clear image of the distant galaxy, we might see multiple, smeared or stretched copies of it, arrayed around the central darkness like a celestial mirage. In the most perfect alignment, where the background object is directly behind the black hole, the light can be bent into a complete circle, a shimmering halo of distortion known as an Einstein ring. This is not a ring of material, but a ring of pure warped light, a perfect geometric signature of spacetime's curvature. But gravitational lensing is more than just a cosmic illusion, it is a tool. The bending of light also magnifies the background object, acting as a natural telescope that can amplify the light of galaxies so distant they would otherwise be invisible. Astronomers actively use this effect to peer deeper into the universe than any human-made instrument could alone. By studying the specific pattern of distortion around a suspected black hole, scientists can actually map its gravitational field and estimate its mass with incredible precision, even if the black hole itself is completely dark. Furthermore, by searching for the characteristic warping of background starlight, we can potentially find isolated black holes drifting silently through interstellar space, black holes that have no accretion disk to betray their presence. Every distorted image, every Einstein ring, is a direct snapshot of warped spacetime, a visible testament to the fact that these giants do not just occupy space, they actively sculpt the very geometry through which light itself must travel. Relativity makes this cosmic gravity not just a force but a sculptor of time itself. Near a supermassive black hole, the most profound distortion is not of space, but of the very seconds and minutes we live by. This is time dilation, a real and measurable effect where gravity slows the passage of time. The stronger the gravity, the slower time ticks. For an object falling toward the event horizon of one of these giants, this creates a paradox of perspective that splits reality in two. Imagine watching a brave, or perhaps foolish, astronaut on a mission to cross the boundary. From your safe vantage point far away with a powerful telescope, you would witness something utterly strange. As the astronaut approaches the event horizon, their clock would appear to tick slower and slower. Their movements would become a gradual, agonizing crawl. Their signals back to you would stretch out, their light shifting to longer and longer, redder wavelengths. At the very moment they reach the point of no return from your perspective, they would appear to freeze completely, a statue etched onto the edge of darkness, their last photon redshifted into invisibility. You would never actually see them cross. To you, the distant observer, their fall takes an eternity, but for the astronaut, the experience is completely different. From their own frame of reference, their watch ticks normally, their heart beats at its usual rhythm, they feel the pull of gravity, and they crosses the event horizon without any dramatic sensory shift at that precise mathematical line. The universe outside, however, transforms before their eyes. As they fall, the light from the external cosmos blue shifts and compresses. They would see the stars and galaxies whirl and streak, their light accelerating into a blinding, frenetic blur. The entire future history of the universe, billions of years of cosmic evolution, could flash before them in a matter of moments from their perspective. It is a one-way ticket to the farthest future, a journey where you leave your own time behind forever. This is not science fiction, but a direct consequence of Einstein's equations. We have already measured this effect on a tiny scale here on Earth. Extremely precise atomic clocks tick measurably faster on a mountaintop, where gravity is minutely weaker than they do at sea level. Near a black hole, that subtle difference becomes a chasm. For the universe's largest black holes, with their immense but gentle gravitational gradients, an astronaut might cross the horizon unharmed, only to find that everyone and everything they ever knew has aged into cosmic dust in what felt like a brief final fall. The spinning heart of a black hole creates a prison of motion called the ergosphere. This is not the event horizon, the point of no return, but a second, larger boundary that exists only for rotating black holes. Picture the event horizon as a perfect dark sphere. Now imagine that sphere being squeezed at the poles and bulging at the equator by the black hole's furious spin, creating a shape like a flattened pumpkin. This outer, oblate shell is the ergosphere. Within this region, something utterly bizarre happens. The black hole's rotation drags the very fabric of space-time around it with such force that nothing, not even light, can stand still. It is a cosmic whirlpool where you are compelled to move. If you were somehow placed inside the ergosphere, you would find it impossible to hover in one spot, no matter how powerful your rockets. You would be swept along, forced to rotate in the same direction as the black hole, caught in the irresistible current of twisted spacetime. This relentless drag is more than a curious effect, it is a potential source of unimaginable power. The physicist Roger Penrose proposed a brilliant thought experiment, now called the Penrose process. Imagine a particle entering the ergosphere. If it were to split in two, with one piece falling into the event horizon and the other escaping, the escaping fragment could theoretically carry away more energy than the original particle arrived with. Where does that extra energy come from? It is stolen from the black hole's own rotational energy. The infalling piece must have what is called negative energy relative to an observer far away, and by dumping this negative energy into the black hole, it slows the monster's spin ever so slightly. The escaping piece rockets off with the extracted energy like a thief making a getaway. While this is a theoretical process for a single particle, nature may perform it on a colossal scale. Many astronomers believe the turbulent dynamics within the ergosphere, where magnetic fields are wound to breaking point, are what channel and launch the relativistic jets that scream from the poles of active black holes. Those galaxy-spanning beams of plasma could be the ultimate expression of energy extraction, a testament to the fact that a spinning black hole is not just a mass but a dynamic battery, its rotation powering the most luminous objects in the cosmos. The ergosphere is not just a zone of forced motion, it is a cosmic bank vault, and the Penrose process is the theoretical blueprint for a heist. This brilliant idea, proposed by the physicist Roger Penrose, shows how a black hole's spin is not just a property, but a reservoir of usable energy waiting to be tapped. The mechanism relies on the bizarre physics within that whirling region of twisted spacetime. Imagine a single particle, perhaps a piece of interstellar dust or a fragment of an atom, drifting into the ergosphere. It carries a certain amount of energy, like a traveler with a specific amount of cash. Now, inside the ergosphere, this particle is compelled to move with the black hole's rotation. In this chaotic, high-energy environment, let us say the particle splits into two fragments. This could happen through a collision or some other violent interaction. Here is where the magic happens. One fragment, through a complex dance of trajectories and energy states, falls across the event horizon and into the black hole. But crucially, from the perspective of an observer far away, this infalling fragment carries what is called negative energy. It is like the particle is depositing an IOU into the black hole's account. To balance the cosmic books, the other fragment must rocket out of the ergosphere, escaping the black hole's grip entirely. And because its partner carried negative energy in, the escaping fragment can carry away more total energy than the original whole particle arrived with. Where did that extra energy come from? It was stolen directly from the black hole's own rotation. The infalling negative energy fragment acts as a brake, slowing the black hole's spin by a minuscule amount. The energy of that lost rotation is transferred to the escaping piece, which blasts away like a bullet fired from a cosmic slingshot. While this exact sequence with a single particle is a thought experiment, it reveals a profound truth. The rotational energy of a spinning black hole is not locked away forever. It is, in principle, extractable. Nature may be performing a scaled-up, chaotic version of this process all the time. The incredible power of relativistic jets, those beams that scream from the poles of active black holes for thousands of light years, might be the ultimate expression of this energy extraction. Magnetic fields tangled in the ergosphere could act like a giant, natural version of the Penrose process, channeling plasma and stealing rotational energy to fuel the most powerful engines in the universe. So while we are not building a power station around a black hole, the theory tells us that these giants are more than dark masses. They are spinning dynamos, their fury a direct conversion of twisted spacetime into raw galactic-scale power. The spinning dynamo of a black hole is not just an engine, it is also a deeply ordered system, governed by laws that echo the most fundamental rules of our universe. This revelation came from an unexpected marriage of ideas, linking the cold, dark giants of gravity to the warm, everyday science of heat and disorder, thermodynamics. For decades, physicists treated black holes as simple, dead-end points, objects that only absorbed and never gave back. This changed in the early 1970s, thanks to the insights of a young graduate student named Jacob Bekenstein. He noticed a troubling paradox. If you throw a box of hot gas, a system with high entropy, into a black hole, that entropy seems to vanish from the universe forever. But the second law of thermodynamics, a sacred pillar of physics, states that the total entropy of the universe can never decrease. It must always increase or stay the same. To resolve this, Bekenstein made a radical proposal. What if the black hole itself has entropy, and what if that entropy is not hidden inside, but is written on its one-way surface, its event horizon? He suggested that a black hole's entropy is directly proportional to the area of its event horizon. The larger the black hole, the larger its horizon, and the greater its entropy. This was a stunning idea. Entropy is a measure of disorder, of hidden information. Bekenstein was saying that the ultimate simplicity of a black hole, its no-hair nature, actually represents the maximum possible disorder for anything of its size. All the complexity of what fell in is smeared into a featureless surface area, a perfect holographic record. Stephen Hawking initially disliked this idea, as it suggested black holes had a temperature and warm things must radiate. But in pursuing this contradiction, Hawking made his own monumental discovery. By applying quantum mechanics to the curved space at the event horizon, he proved that black holes do, in fact, radiate. They have a temperature, now called the Hawking temperature. This temperature is inversely related to the black hole's mass. A stellar mass black hole has a tiny, barely measurable temperature, while a supermassive black hole's temperature is far colder than the cosmic background, meaning it absorbs more heat than it emits. This completed the profound link. Black holes obey the laws of thermodynamics perfectly. Their horizon area is entropy. Their Hawking radiation gives them temperature. And their mass is equivalent to energy through Einstein's famous equation. This connection between gravity, quantum mechanics, and thermodynamics is more than a neat analogy. It is a blazing signpost pointing toward a deeper, unified theory of reality, a theory of quantum gravity that might one day explain the birth of the universe itself from a single, profound equation. This link between entropy and surface area is a clue to a much deeper truth about reality itself. It hints that the universe may operate on a principle so strange it sounds like science fiction, the holographic principle. To understand this, we must return to the black hole information paradox, the puzzle of what happens to the information of everything that falls in. The holographic principle offers a breathtaking solution, one that reimagines the very nature of space and information. It proposes that all the information needed to describe everything within a three-dimensional volume of space, including every star, planet, and atom that ever crossed a black hole's event horizon, is not stored inside that volume at all. Instead, it is encoded on the two-dimensional boundary surrounding it like a hologram. For a black hole, that boundary is its event horizon. Think of a standard hologram on a credit card. It is a flat, two-dimensional surface, but when light shines on it, it projects a full, three-dimensional image. The holographic principle suggests that our entire three-dimensional reality and everything in it might be a similar kind of projection. The true, fundamental description of the universe could be written on a distant, two-dimensional surface, with our rich, volumetric experience being an emergent illusion. In the case of a black hole, this solves the information paradox elegantly. When matter falls in, its information is not destroyed at the singularity. It is scrambled and imprinted onto the rippling quantum fabric of the event horizon itself, stored in the microscopic Planck-scale pixels that make up its surface area. Hawking radiation, then, is not random thermal noise. As the black hole evaporates, this encoded information on the horizon can, in theory, be slowly and chaotically released back into the universe through the radiation, preserving the total information content. The information was never inside the black hole in the conventional sense. It was always on its skin, waiting to be read back out. This idea transforms a black hole from a cosmic trash compactor into the universe's most extreme data storage device, a sphere where the interior is a projection of the data written on its surface. If true, it means the largest black holes in the cosmos are not just gravitational titans, but the ultimate holographic plates, their immense horizons holding the quantum blueprints for everything they have ever consumed. Even the mightiest structures in the cosmos have an expiration date. The relentless quantum whisper of Hawking radiation ensures that no black hole is truly eternal. For the supermassive and ultramassive giants we have been discussing, this is not a death sentence, but a slow, inevitable fade into the cold. The timescale, however, is so vast it defies all human intuition. A black hole with the mass of our Sun would take many orders of magnitude longer than the current age of the universe to evaporate. But for a monster weighing billions of solar masses, the clock is set to a duration that is essentially forever and then some. We are talking about timescales on the order of 10 to the 100th power years. That is a 1 followed by 100 zeros, a number so large it has no name in our mathematics. To grasp this, consider that the entire history of our universe from the Big Bang to today is roughly 10 to the 10th power years. This future timeline is 10 to the 90th power times longer than everything that has ever happened. In that distant, dark epoch, all stars will have burned out eons ago. Galaxies will have evaporated, their stars either dead or flung into the intergalactic void. The universe will be a profoundly cold and empty place, a thin soup of subatomic particles and photons stretched to impossibly long wavelengths. And in this silent, frozen expanse, the last supermassive black holes will still be there, dark monarchs in a dead kingdom. But even they are not permanent. As the universe cools further, their Hawking radiation will finally overcome the faint warmth of the cosmic background. They will begin to lose mass, slowly at first, then faster and faster as they shrink. In their final moments, a black hole with the mass of a mountain will release the energy of 1,000,000 hydrogen bombs in a sudden, brilliant flash of gamma rays. But for our billion solar mass titans, that final pop will be a faint, almost imperceptible sigh in an utterly dark and empty cosmos, the last meaningful event before eternity truly begins. Their evaporation marks the end of the era of structure, a final transition into a universe where gravity's great sculptures have all melted away into a uniform, featureless sea of fading energy. Their eventual evaporation is a story for an unimaginably distant future, but their brilliant youth serves a vital purpose for astronomers right now. The most luminous quasars powered by these monstrous black holes are not just objects of study, they are tools. Their incredible brightness makes them the perfect cosmic lighthouses, beacons visible from the farthest reaches of space and time. Astronomers use them as backlights to illuminate the universe's hidden architecture. When the intense light from a distant quasar travels billions of light years to reach us, it does not pass through empty space. It cuts through a vast, invisible web of diffuse gas clouds, the faint filaments of hydrogen that stretch between galaxies, tracing the cosmic web of dark matter. As this quasar light passes through these clouds, specific wavelengths are absorbed by the hydrogen atoms, leaving dark lines in the quasar's spectrum, its rainbow of light. These are not single lines, but a dense, complex thicket of absorption features, a phenomenon astronomers poetically call the Lyman alpha forest. Each dark line corresponds to a specific cloud of hydrogen at a specific distance along the line of sight. By measuring the redshift of each absorption line, scientists can determine how far away each intervening cloud is. The result is breathtaking. A single beam of light from one quasar creates a one-dimensional core sample through the universe, a timeline of gas clouds stretching from the quasar's own epoch all the way to our telescopes. Now imagine doing this for thousands of quasars scattered across the sky. Each one gives you a thin, pencil beam slice of the cosmos. By combining them, you can stitch together a three-dimensional map of the universe's large-scale structure, a tomographic image of the cosmic web itself. This map reveals the vast, bubble-like voids and the dense, filamentary walls where galaxies congregate, a blueprint of creation drawn in shadow and light. In this way, the universe's largest black holes, through the brilliant fury they create, become the ultimate surveyors, their light acting as a probe that charts the invisible skeleton of everything that exists. Their brilliant fury creates not just light but a cosmic echo chamber. Deep within the chaotic heart of an active supermassive black hole, the inner edge of its accretion disk is a maelstrom of violence. Gas heated to millions of degrees and whipped to near light speed doesn't fall in smoothly. It crackles with sudden, intense flares of X-rays like cosmic lightning erupting from the edge of the abyss. These brilliant flashes do more than just announce the black hole's activity. They act as a strobe light, illuminating the entire hidden architecture of the black hole's immediate neighborhood. The X-rays blast outward, striking the dense, slower-moving clouds of gas that orbit farther out, a region known as the broad line region. These clouds, in turn, absorb the high-energy light and re-emit it at specific characteristic wavelengths, a process called fluorescence. It is as if the inner disk shouts and the surrounding gas shouts back, but there is a delay. The light from the flare travels outward to the gas clouds, and then the re-emitted light must travel back toward our telescopes. That tiny lag, that interval between the initial X-ray flash and the answering glow from the clouds, is the echo. It is a delay of mere minutes or hours, but in that minuscule gap lies a universe of information. This technique is called X-ray reverberation mapping, and it is one of the most precise tools we have for measuring the anatomy of a monster. By meticulously tracking the time delay for different parts of the re-emitted light, astronomers can perform a form of cosmic triangulation. They can calculate the precise distance from the flaring inner disk to the echoing gas clouds. This allows them to map the three-dimensional geometry of space just outside the event horizon with astonishing accuracy. It is like using sonar to chart the contours of an underwater canyon, but here the sound is light, and the canyon is carved by gravity so extreme it warps time itself. Through these echoes, we are not just observing a black hole. We are listening to the reverberations of space-time, using the delay of light itself to trace the shape of the darkness. Those brilliant jets of plasma are not just propelled by gravity alone. Their formation and incredible focus require an invisible hand, a force so powerful it can channel matter to nearly the speed of light. That force is magnetism. The relativistic jets screaming from the poles of supermassive black holes are not random explosions. They are precision-engineered beams, and their secret lies in the generation of monstrously strong, perfectly organized magnetic fields. This is one of the great unsolved details in our understanding of these cosmic giants. We know the fields must exist, but how are they created and sustained in the absolute chaos surrounding a black hole? The environment is a swirling, superheated hurricane of plasma, a gas so hot its atoms are torn apart into a soup of charged particles. In this maelstrom, the magnetic fields cannot be simple static structures. They are alive, woven into the very fabric of the moving plasma, twisting, snapping, and reconnecting in a frenzied dance. The study of this chaotic interplay is called magnetohydrodynamics, or MHD, a complex fusion of magnetism and fluid dynamics. To unravel this mystery, scientists cannot build an experiment here on Earth. Instead, they construct virtual universes inside supercomputers. These MHD simulations are some of the most demanding calculations in all of science, modeling billions of particles and the evolution of magnetic field lines in the violently curved spacetime near an event horizon. The leading theory is called the Blandford-Zienagic process. It suggests that the black hole's own spin is the ultimate power source. Imagine the black hole as a spinning conductor, dragging the fabric of space and the magnetic field lines anchored in the surrounding accretion disk. This dragging twists the magnetic fields into a tightly wound coil, a cosmic spring loaded with energy. Near the poles, these wound-up field lines can snap open, creating a funnel that accelerates and collimates the jet, like squeezing a tube of toothpaste with incredible force. But the simulations reveal a problem: sustenance. The chaotic inflow of plasma should tangle and weaken these delicate magnetic structures, yet the jets we see are stable for thousands of years. How does the system maintain such perfect order within the storm? The answer might lie in the accretion disk itself. Some simulations show that the disk's rotation can act as a dynamo, constantly generating and reinforcing the magnetic field, a self-sustaining cycle where motion creates magnetism, which in turn channels the motion. It is a delicate, cosmic balancing act happening at the edge of oblivion, and solving it will reveal how the universe's darkest hearts generate its most brilliant, focused light. The most violent explosions since the Big Bang are not the work of supermassive giants. Gamma-ray bursts are the universe's ultimate flashbangs, brief but unimaginably powerful blasts of the highest energy light, capable of outshining entire galaxies for a few fleeting seconds. And while they are a testament to extreme physics, they are often mistakenly linked to the largest black holes. The truth is more specific and more fascinating. These cosmic detonations come in two distinct flavors, each with its own dark creator. The first and most common are long-duration gamma-ray bursts lasting from 2 seconds to several minutes. These are not the signature of a supermassive black hole's feeding frenzy. They are the final, dying scream of a single colossal star, many times more massive than our Sun. When such a star exhausts its fuel, its core collapses not into a peaceful neutron star, but directly into a stellar mass black hole. The infalling outer layers of the star slam into this newborn singularity, and in a fraction of a second, the energy is focused into two narrow, oppositely directed jets of ultra-relativistic particles. If one of those jets is pointed directly at Earth, we see it as a long gamma-ray burst, a beacon signaling the violent birth of a relatively small black hole from a single star's death. The other type, short-duration gamma-ray bursts, last less than 2 seconds and pack their energy into an even more concentrated punch. These are thought to be the signature of a different and even more catastrophic stellar-scale event, the merger of two neutron stars. As these ultra-dense stellar corpses spiral together and collide, they can create a black hole in a single, spectacular instant. The resulting maelstrom of matter and magnetic fields for a blinding moment becomes the brightest object in the gamma-ray sky. So while the supermassive black holes at galactic centers are steady, long-term engines, the gamma-ray burst is a sudden, stellar-scale detonation, a flashbulb pop marking the creation or transformation of a much smaller, but no less violent, gravitational pit. It is a crucial distinction, one that reminds us black holes come in all sizes, and each class writes its signature on the cosmos in a different, brilliant script. The final union of two titans is not always a clean merger. Sometimes it is a violent recoil that launches the resulting monster into the void. This is the black hole kick, a consequence of the most asymmetric and chaotic collisions in the universe. When two supermassive black holes spiral together, their final moments are governed by the intricate geometry of their spins. If those spins are aligned with each other and with the orbital plane, the merger is relatively smooth and the gravitational waves radiate away symmetrically. But if the spins are tilted, misaligned, or pointing in wildly different directions, the last moments become a chaotic lurch. The emission of gravitational waves becomes heavily unbalanced, like a rocket firing more strongly out of one side than the other. This asymmetry imparts a tremendous net momentum to the final, single black hole, literally kicking it like a cannonball. The speeds involved are not just high, they are galactic escape velocities. Simulations show these kicks can reach 5,000 kilometers per second or more, enough to fling a billion solar mass objects straight out of its host galaxy's core and into the intergalactic darkness. This creates a rogue black hole, a homeless giant drifting silently between the stars, stripped of its accretion disk and any visible trappings of power. For astronomers, the hunt for these dark exiles is a compelling cosmic detective story. The evidence is indirect but telling. We might see a galaxy with a bright, active nucleus that is visibly offset from its exact center, as if the engine has been knocked askew. Or we might find a galaxy with all the hallmarks of a recent merger: distorted structures, tidal tails of stars, but with no supermassive black hole detected at its heart, just an unexplained emptiness where the gravitational anchor should be. These are the ghostly signatures of a kick, a reminder that even the most massive objects in creation are not immune to the violent recoil of their own birth, cast out from their thrones to wander the endless night alone. Not every cosmic giant hides in the distant past. Some rule from a throne we can see with startling clarity. In the relatively nearby universe, a mere billion light-years away, sits the galaxy IC 1101, a true monarch of the local cosmos. It is not a graceful spiral, but a colossal, golden elliptical, the single largest galaxy we have ever discovered. Its size is almost incomprehensible, a sprawling swarm of stars spanning over 6 million light-years from edge to edge. To put that in perspective, if you placed IC 1101 where our Milky Way sits, it would swallow not only our galaxy, but Andromeda, the Triangulum Galaxy, and every other member of our local group, with room to spare for dozens more. This is a galaxy built from a history of unimaginable cannibalism, the final product of countless mergers in the dense heart of its galaxy cluster. And at the very center of this stellar empire, anchoring its unimaginable mass, lies a black hole of equally staggering proportions. Estimates for this dark heart vary, as measuring such a beast is a monumental challenge, but the numbers are consistently jaw-dropping. Current studies suggest a mass between 40 and 100 billion times that of our Sun. This places it firmly in the ultramassive category, a rival to the legendary TON 618, but with a crucial difference. While TON 618 is a brilliant, furious quasar from the universe's youth, the black hole in IC 1101 is a quieter, more mature giant. Its relative proximity offers us a priceless opportunity. We are not looking at a brilliant, blinding beacon from the ancient past. We are looking at a settled king in its current domain, a system where the frantic growth has slowed, allowing us to study the anatomy of an ultramassive black hole in a more stable state. We can observe the subtle effects of its gravity on the surrounding stars, map the faint, residual heat of its surroundings, and piece together how such a monster interacts with its equally monstrous galaxy in the calm after an eon of feasting. IC 1101 is our local laboratory for understanding the ultimate endpoints of galactic evolution, a dark heart close enough to whisper its secrets if we know how to listen. At the very center of these cosmic giants lies a paradox of impossible scale. We have spoken of their immense mass, their vast horizons, and their twisting spacetime, but all of that leads to a single, inescapable point. According to Einstein's theory of general relativity, every particle of matter that falls into a black hole is crushed inward by gravity, traveling along all possible paths to a final destination. That destination is the singularity, a point of infinite density where the very concepts of space and time cease to have any meaning. the equations of relativity, which work so perfectly to describe the warped space around the black hole, produce a result that is essentially a mathematical scream, a sign that the theory has reached its limit. An infinity in physics is not an answer, it is a failure of description. It tells us that something profound is missing from our understanding. This is not a small gap in knowledge, it is a chasm at the heart of our most successful theory of gravity. The singularity represents a place where the rules of the very large, the domain of planets and galaxies governed by relativity, collide with the rules of the very small, the bizarre, probabilistic world of quantum mechanics. And in that collision, our current physics shatters. This is why black holes are more than astronomical objects. They are the ultimate laboratories for a revolution we have not yet completed. They are screaming at us that we need a new theory, one that can marry the force of gravity with the rules of the quantum realm. This unified theory is called quantum gravity, and it is the holy grail of modern physics. Without it, the center of every black hole, from the smallest to the largest, remains a blank spot on the map of reality, a place where our science simply stops. The quest for this theory has given rise to some of the most imaginative and mathematically complex ideas in human history, like string theory, which proposes that the fundamental particles of the universe are not points but tiny, vibrating strings, and loop quantum gravity, which suggests that space itself is woven from a fabric of finite, interlocking loops. These are not just abstract games, they are attempts to answer the question posed by the singularity, to describe what reality is like under conditions of such extreme curvature that space and time become granular, like the pixels on a screen. The universe's largest black holes, with their gentle gravity gradients, offer a unique window. Their singularities, while still points of infinite density, are buried deep within a vast, calm space, potentially giving us a cleaner mathematical environment to test these radical ideas. By studying the shadows and echoes of these giants, we are not just learning about black holes, we are probing the fundamental architecture of the universe, searching for the laws that will write the final chapter in the story of gravity itself. That iconic image of the cosmic donut holds a subtle but crucial secret. The dark heart at the center of the glowing ring is not the event horizon. It is something even more profound, a black hole's shadow. This distinction is everything. The event horizon is a mathematical boundary, the point of no return. It is invisible by definition, a line in space you could never actually see. What the Event Horizon Telescope captured is the silhouette this boundary casts against the brilliant firestorm behind it. Think of holding your hand up to a bright lamp. You see the shadow of your hand on the wall, a dark shape larger than your hand itself. The black hole does the same thing with spacetime. Its immense gravity bends the paths of light from the hot gas swirling behind it, wrapping those light rays around itself and trapping them. The result is a central region of darkness, a shadow where light from the background simply cannot reach your eye. This shadow is not empty space. It is a prison of bent light paths, a perfect manifestation of warped geometry. And its size is a precise prediction of Einstein's theory. For a simple, non-spinning black hole, the shadow's diameter is about 2.5 times larger than the diameter of the event horizon itself. That dark circle we all saw in the image of M87 star, and later in Sagittarius a star, is that shadow, a fingerprint of gravity so strong it bends light into a circle of perfect darkness. It is the closest we can ever come to seeing the unseeable, not the point of no return, but its dark echo against the light of the cosmos. The light from these brilliant quasars is a message from the universe's youth, a cosmic telegram that took billions of years to arrive. When we point our telescopes at a quasar like TON 618, we are not seeing it as it is today. We are witnessing it as it was over 10 billion years ago, when the cosmos was less than a third of its current age. This makes them more than just distant monsters. They are perfect time capsules, preserving a snapshot of an era known as cosmic noon. This was the universe's wild, formative period, a time of incredible fecundity and violence. Galaxies were smaller, closer together, and brimming with fresh, cold gas. It was the peak epoch of star formation, a golden age when new suns were igniting at a rate far greater than today. And at the heart of this bustling cosmic construction site, supermassive black holes found a banquet laid out before them. The abundant gas funneled into their cores, igniting the brilliant fury of quasars that lit up the early darkness like beacons. By studying the specific light from these ancient quasars, astronomers can read the conditions of that long-vanished time. The absorption lines in their spectra, the Lyman alpha forest we discussed earlier, act as a chemical fingerprint. They reveal the composition and temperature of the diffuse gas that filled the space between young galaxies, telling us what the raw material of creation was like. They show us how heavy elements, forged in the hearts of the first stars and scattered by supernova, were gradually enriching the cosmos. Each quasar is a single, brilliant pinprick that illuminates a one-dimensional core sample through billions of light-years of cosmic history. But by observing thousands of them scattered across the sky, we can stitch together a three-dimensional map of the early universe's large-scale structure. We can see the faint outlines of the cosmic web beginning to form, the vast filaments of dark matter along which the first galaxies would assemble. In this way, the most violent and energetic objects in existence become our gentlest historians. Their furious light, generated by matter screaming its last as it falls into oblivion, carries a pristine record of the universe's childhood, a story of birth and growth written in the shadows cast by the darkest things we know. Our catalogue of cosmic giants is far from complete. For every ton 618 we have found, there may be a dozen more lurking in the distant dark, monsters whose light has not yet reached us or whose quiet nature hides them from our current view. The search for the universe's largest black holes is accelerating, driven by a new generation of telescopes that will redefine the frontiers of astronomy. On a mountaintop in Chile, the Vera C. Rubin Observatory is preparing to conduct the Legacy Survey of Space and Time, a 10-year cinematic portrait of the sky. Its massive mirror and giant digital camera will scan the heavens with such speed and depth that it will detect millions of new quasars and tidal disruption events, transient flares that betray the presence of otherwise dormant supermassive black holes. It will find them in places we have never thought to look, in small galaxies or wandering alone in the void, expanding our map of these dark hearts by orders of magnitude. Meanwhile, the Nancy Grace Roman Space Telescope will turn its powerful eye toward the deep past. With a field of view 100 times larger than the Hubble Space Telescopes, it is designed for cosmic archaeology. It will peer into the era of the first galaxies, hunting for the faint, redshifted glow of the earliest quasars, the seeds from which today's giants grew. By finding them, we will finally understand the black hole seed problem, witnessing the infancy of the monsters. Together, these instruments will comb the cosmos, and what they find may shatter our current records. We stand on the brink of discoveries that could reveal black holes with masses of 100 billion or even 1 trillion solar masses, behemoths that push against the theoretical quasar limit and force us to rewrite the rules of growth. The story of the universe's largest black holes is not a finished book. It is a living narrative, and the next chapter, written in data from these new eyes on the sky, will reveal giants that make our current champions seem almost modest by comparison. From the staggering scale of ton 618, a gravitational sphere wider than our solar system, to the controversial, potentially 100 billion solar mass behemoth in the Phoenix cluster, we have measured monsters whose weight is written in the frantic dance of stars and the echo of hot gas. We have seen how their furious spin twists spacetime itself, powering relativistic jets that sculpt galaxies for millions of light years, and how their silent mergers send shudders through the fabric of reality, a gravitational wave symphony we are just learning to hear. We have confronted the paradox at their heart, where information seems to vanish into a singularity, screaming for a new physics that can unite the vast and the quantum. This journey reveals a truth far more profound than simple destruction. These cosmic giants are not mindless voids. They are fundamental architects. They govern the birth of stars within their galaxies. They regulate galactic growth through brilliant, violent feedback, and their ancient light serves as a beacon, illuminating the large-scale structure of the entire cosmos. They are the dark hearts around which the visible universe organizes itself. So the next time you look at the night sky, remember, in the heart of darkness lies the key to understanding light itself. If one of these facts reshaped your view of the cosmos, let us know which one surprised you most in the comments below. For more journeys to the edge of understanding, be sure to like, subscribe, and join us as we continue to explore the universe's greatest mysteries.